Hi, my name is Joe Chacon. I'm an electrical engineer with Padge LLC. This is the fifth of several videos about harmonics. Today, I want to talk about how a line reactor can mitigate harmonics and give an example. I must clarify that I am not a magnetic design specialist. I do well with applications, but not with the design itself. Please look back at the previous videos to get a background for this video. Let's start with how line reactors are rated. I'm only going to focus on line reactors for this video, but load reactors are also very similar from a physics perspective. Line reactors are usually rated by their impedance as a percentage value, their amperage rating, and their voltage rating. If they are rated off of horsepower or kVA, then voltage and amperage can be calculated. Let's start with an example. Suppose we have a line reactor with 3% impedance rated for 150 amps and 480 volts AC. What does the 3% impedance mean? 3% of what? Practically, it means the line-to-line voltage drop across the reactor is 3%. So for 480 volts AC, the voltage drop is 0.03 times 480, which is 14.4 volts. We need to convert this to line to neutral voltage drop, which is line to line voltage divided by the square root of 3. So 14.4 volts divided by the square root of 3 is 8.31 volts. Now, we want to derive our reactance, which is Ohm's law. Our voltage, 8.31 volts divided by our current rating of 150 amps is 0.05545 ohms. This is 147 microhenries when expressed as inductance. I trust you remember the formula for reactance as 2 times pi times frequency times inductance. I said it in a previous video, inductance is constant, but reactance varies as a function of frequency. The reactor will go on the line side of a 6-pulse variable frequency drive. We looked at 6-pulse rectifiers in a previous video. The approximate horsepower of our motor is 125 horsepower. Horsepower has a lot of assumptions in its calculations, such as efficiency, power factor, and line voltage. Always try to understand the assumption. Let's assume that our motor and variable frequency drive will put 130 amps on the line side. In video 2, we saw how to drive harmonic content for a 6-pulse rectifier. There are a lot of other system interactions that can create additional harmonics. With that said, we calculated 20% on our 5th harmonic, 14% on our 7th harmonic, and 9% on our 11th harmonic. Let's just stay with those numbers. That's a lot to remember for the assumptions. So this chart will help us remember. Now that we have everything written down and we know our line reactor's inductance, we need to calculate the reactance each harmonic. So you can see reactance on the fundamental, reactance on the 5th, reactance on the 7th, reactance on the 11th. Now let's calculate filtered harmonic percentage based off the initial harmonic content. And look at how effective the filtering is. The filtered 5th ends up being 4%, filtered 7th, 2%, the filtered 11th, 0.8182%. Please reference video 1 on how to calculate total harmonics distortion, called THD. Now, in this case, the THD before installing the line reactor was 26.0%. And the THD after installing the line reactor is 4.5%. Suppose you wanted a 5% impedance reactor instead of a 3% impedance reactor. Well, if you do the math, you'll see that makes the inductance 245 microhenries instead of 147 microhenries. But does that change the THDI or total harmonic distortion current? The answer is no, it does not. Since the filter percent values do not change at all, why would we want to go with the 5% impedance then? Suppose we're connected to a weaker grid, perhaps an on-site generation system. Let's say our source impedance for our grid is 0.2 ohms. We now need to calculate our voltage harmonics and not just our current harmonics. Our voltage harmonics are calculated at the point of common coupling. You'll see I talk about this in a lot in a future video when I show software tools for analyzing harmonics. We call the point of common coupling PCC. Ohm's law gives us these values for each harmonic, knowing our source impedance is 0.2 ohms. We calculated our 3% reactor reactances for the fundamental and the 3 harmonics. Remember, there were 0.2771 ohms for the 5th, 0.3879 ohms for the 7th, and 0.6096 ohms for the 11th. I put them in this chart and also calculate the reactances for the 5% reactor. We said the source impedance was 0.2 ohms, so we will add that to the individual harmonics impedances respectively. One way to show the harmonic content for the 5% reactor is to use the impedance ratio between the total impedance for the 3% system and the 5% system. For example, the ratio of the impedances between 3% system on the 5th harmonic and the 5% system on the 5th harmonic is 0.721. We know the 3% system has 26 amps on the 5th harmonic because 20% of 130 amps is 26 amps. We defined the harmonic content earlier. When we put the impedance ratios in place, we can see 3% and 5% harmonic content in this chart. We multiply each of these harmonic contents times the source impedance to derive the voltage for each harmonic. This is just Ohm's law. Once we do that, we can calculate the total harmonic distortion called THDV at the point of common coupling. That comes out to be 2.4% for the 3% reactor and 1.7% for the 5% reactor. So in this case, the 5% reactor would be a bit of overkill. I took the liberty of increasing source impedance for our example, 3% reactor to see where would we want to buy 5% reactor. This chart shows source impedance would need to be quite high for our example. Finally, line reactors also oppose rapid change in current. The voltage drop across them is the first derivative of current times the reactor's inductance. I made this plot in Excel to show a current spike without the reactor in place and with the reactor in place. Since di dt times inductance is voltage, I hope you can see how the reactor also limits voltage spikes. If the spike is external, let's lightning, for example, the inductor will not limit this type of voltage spike. I hope it is a bit clearer as to how harmonics can be mitigated by passive line reactors. I hope this knowledge can help you become the harmonics guru in your company. Please look us up at padge.org. That's padge.org if you need anything on this topic or others.